I'd like to introduce Korbinian Staudacher to give us a talk on multi-controlled phase gate synthesis with the ZX calculus applied to neutral atom hardware. Take it away, Korbinian.
Okay, yeah, thanks for the introduction. Let me just quickly share my screen. And so, okay, do you see my screen?
Yep, we can see it.
Okay, fine. So thanks a lot, and thanks a lot for the opportunity to have me here in the ZX seminar that I can speak about the paper. So I'm Korbinian Staudacher. I'm working in Munich, and I will be talking today about this paper titled Multi-Controlled Phase Gate Synthesis with ZX Calculus Applied to Neutral Atom Hardware. So what this mainly is about is a synthesis algorithm for a certain hardware, which is the neutral atoms hardware. So when we talk about synthesizing quantum circuits, we usually talk about having as input some hardware agnostic quantum circuit, which is not tailored to any basis gate set we have on different devices. And then we have this synthesis algorithm, and then we map this circuit towards a gate set which is present on a certain hardware, like in superconducting hardware, C0 and single qubit rotation. On ion traps, usually something which involves a Mølmer Sørensen gate. And on neutral atoms, we have two specialities regarding the gate set. What we will consider is a native gate set consisting of both fast local Z rotations, but on the other hand, slow X or Y rotations, or arbitrary other rotations, which are only global, which we can only apply on all qubit at once. And the second thing is that we can have multi-qubit interactions between qubits. So not only C0 and CZ on 2 qubits, but on more than 2 qubits natively. And so this work will be mostly dealing with the third aspect, that we have this opportunity to have multi-controlled phase gates. So the first thing I will talk about is a ZX calculus-based algorithm to synthesize exactly those controlled phase gates. And for that, we use graph-like diagram simplification, this thing here. And with this synthesis algorithm, we then end up in a gate set which consists of RZ, Hadamard, and controlled phase rotations. And as a second step, since those Hadamard gates cannot be natively implemented on neutral atom hardware, we apply a known decomposition scheme of those single qubit gates to alternating global rotations and local Z rotations. So as a start, I want to first a bit shortly highlight the points of how a neutral atom hardware usually looks like. So this is a typical setup we are currently also more or less building in Munich. So the main point is that we trap neutral atoms in so-called optical traps with lasers in a 2D rectangular grid in here. And then we have several laser sources here around, which we can use to modify those atoms. So we have, for the local Z rotations, we have here a laser which can individually address those single atoms guided by acousto-optic deflectors. And there we can modify the qubits locally. But for there we can only do Z rotations, but for those other rotations, we have here this microwave pulse generator, which only can globally address this whole register of atoms. There we can rotate around an arbitrary axis on the Bloch sphere, but it's global. And For measuring, which I also find quite interesting, is we simply take a photo, more or less. So based on the reflectivity here of those atoms, they are fed into a camera and we detect whether some atoms are there or not. And for two-qubit interactions, we usually use a two-photon transition where we excite those individual atoms here with two laser pulses here, this laser pulse and this laser pulse. And we then bring the atoms into a so-called Rydberg excitation. And how this looks like on an energy diagram is that we have here our two basis states encoded in some energy levels of the atoms. And with those Rydberg excitation, the state resonates with the one state. And if our atom is in the one state, it gets shifted to this very high energy state, the Rydberg state. And now we have the peculiarity that if two atoms are very close to each other, they cannot be both in the Rydberg state at the same time because we have a strong van der Waals force between those Rydberg, so between the electrons here, because they are so far away from the nucleus, so that two atoms cannot be in the Rydberg state at the same time. And this we can use then to generate a control Z gate, because then the Cat11 state picks up a different phase. And here you see that it actually not only the 1-1 state picks up a phase, but those states here as well. But we can account for this phase theta with just correcting this with local Z rotations. And this then results in a version which we can pretty much use for a ZZ gate. But also, which I want to emphasize here, this angle here is not fixed to pi. So this can be really experimentally adapted, that it doesn't just rotate about pi, but about pi/2, pi/4, whatsoever. And this is something we will also take into account in our synthesis algorithm. Regarding the multi-qubit interactions, this is experimentally also quite feasible already. They are realized with a similar scheme than the two-qubit, the two-qubit pattern I've shown before. And the nice thing is that this is somehow still faster than single-qubit global rotations, so the XY rotations. And it more or less scales linearly. So even if we go to a higher number of qubits, so not only CZZ, but CZZ, and so on, the gate time does not increase exponentially or something, but it really increases linearly. So we are expecting that even if we have those high number of control qubits, it will be still faster than the global XY rotations. So now we are thinking about how can we exploit this in a synthesis algorithm. And what we did was we used the known scheme of the graph-like diagram simplification and extraction to a gates based on ZX calculus. And the scheme, I think, came already out 4 or 5 years ago. This is by John, Alex, I think Simo Pedri also, and Ross Duncan, where we take a quantum circuit and we transform it to the graph-like version in ZX calculus. So this means we have only those green spiders here, and the green spiders are only connected by a Hadamard between themselves. And now we can use this these graph-like transformations to simplify the diagram and remove some vertices, for instance, with the local complementation, where we can remove an interior spider with phase pi/2 or minus pi/2 by just deleting it and flipping the edges of the neighbors. They get connected if they were not connected before, and vice versa. And similarly, we can use pivot to get rid of pairs where two spiders have either a phase of 0 or pi. And then the edges between the neighbors also flip in some certain way. And most importantly, in our case, or I will explain that later why that is important, is that if we apply the pivot on a pair of spiders where one spider has a non-Clifford phase, we get a so-called phase gadget here. So a phase gadget is simply, it has like a top spider, which is only connected to a single other empty spider, which we call like the root spider here. And this root can be connected to arbitrary neighbors. But the important thing to recognize is that we have this top spider, which has some phase, and it's only connected to a single spider. So there, it's easily distinguishable from other spiders. So now this is already also a kind of standard algorithm in that field, is how do we, after this graph-like simplification, get back a quantum circuit. So what we can do in extraction is to extract it with an algorithm which only works if the diagram admits some kind of flow from measurement-based quantum computing. So that means we interpret this diagram as a measurement pattern where each spider contains or corresponds to an individual qubit. And we can see this by taking this underlying graph here. And if now we find some order of how we can measure those individual qubits and correct unwanted measurement results on further measurements, if that is possible, if we have this order, like given here, we can extract the diagram as well. And I think for this talk, it's not so important to understand how this measurement-based quantum computing and flow really works. It's just important to notice that a phase gadget actually translates in this scheme to a measurement in the YZ plane in the Bloch sphere, not the XY plane in the Bloch sphere. And this will be important later. So now we can proceed with standard techniques to extract a quantum circuit from this diagram. So we start at the outputs and look for gates which we can, or we look for spiders in the diagram which we can directly extract as gates. So this would be, for instance, here a pi/8 phase in this Z spider we can simply extract as an RZ gate, a Hadamard wire which is connected only to another spider here from the outputs, we can directly extract this as a Hadamard gate. And if we have a wire between two outputs, we can directly extract this as a control Z gate. And there are two more involved rules, I would say, which we need to apply in this extraction algorithm, which is first, if we come to such a point where we don't have a single neighbor of one of those outputs, we cannot simply proceed by extracting those edges here as Hadamards, but we need to do something different. So one thing we might need to do is to resolve those YZ vertices, so those phase gadgets, to XY measurements again. And we can do this by applying a pivot between an output and the phase gadget itself. And then we transform this to an XY measurement again. And the nice thing is that if we have only XY spiders and the outputs here, we can find a series of C0 row additions where we here place C0s on the circuit so that we can add up the wires here between outputs and neighboring spiders so that only an output remains which has a single neighbor. And then we can proceed with the standard procedure, extracting this as a Hadamard gate, extracting this as a C phase, and so on. So this is just important to notice that we can always extract a diagram using these steps. And we usually resolved those YZ vertices with the pivot on an output and the phase gadget itself, which kind of revokes the simplification advantage we got before, because we got to the phase gadget when with applying a pivot, and now when extracting it, we are kind of reversing this again when applying a pivot. So now the question I want to address is, how do we incorporate into this? Because here we only extract C0s, C phase, CZs and Hadamards and single qubit gates. How can we incorporate this into extracting multi-controlled phase gates? Therefore, we need to look a bit closer at how a phase gadget really looks like, because we can represent a multi-controlled phase gate exactly as a combination of those phase gadgets. So a phase gadget realizes this transformation where we have given some basis state here, and we apply a phase if the XOR sum here of the individual zeros and ones in the state is odd. And if it's even, nothing happens. So for instance, if we have here as an example, this phase gadget with pi/4, and which is connected to two outputs here, we realize this transformation, e to the power of I times pi/4, x1, XOR x2. And then this phase of e to the power of I pi/4 gets only applied to those basis states which have exactly a single one and not two, like here, and not zero. So this would result in this matrix here. And what can be realized by phase gadgets is always just a diagonal matrix. Now we can really very simply extend this to realize controlled phase gates. Here in this 2-qubit case, we just place phases of phase alpha to the outputs, and we apply a negative phase here, minus alpha, on the phase gadget itself. Because then what we get, this is the following term. This is here the e to the power of I alpha x1 for this, e to the power of I alpha x2 for this. And for the phase gadget with the minus alpha, we get this term here, which is already known from the previous slide. It's the same XOR term. And we can then just sum it all together, and we get this term, e to the power of I alpha x1 plus x2 minus the XOR of both. And if we take those to be Boolean variables, which they are, because we are talking about basis states here, we can use this identity that x1 plus x2 minus x1 XOR x2 always is equal to 2 times x1 x2. And this is what we really want to have for a multi-controlled phase gate, because here we have this multiplication, and this, of course, only is equal to 1 if really both x1 and x2 are equal to 1. So what we get is this matrix where only for the basis state ket1, 1, we get a phase shift about e to the power of I 2 times alpha. And we can generalize this to multi-controlled phase gates as well. This looks a bit more complicated, but it is still the same pattern. So in here we have a phase gadget connected to all of the 3 outputs with a positive alpha, and we have 3 phase gadgets connected to only 2 outputs with negative alpha, and they are connected basically to all possible combinations of the outputs. So 1 and 2, 1 and 3, and 2 and 3. And of course, the outputs also already have this phase alpha. What we then get is the term, which is, I think, more or less the same than on the previous slide. We can translate this using this Boolean identity function to this term here, where we get e to the power of I alpha times 4 x1, x2, x3. And this is again the thing what we want for a multi-controlled phase gate, because we get only this phase shift of e to the power I 4 times alpha on the state get 1, 1, 1. So you might observe that we already we get this factor here for the normal C phase gate. We got a 2 times alpha. For the 3-qubit case, we get a 4 times alpha. So this kind of indicates already that this scales exponentially with this angle of alpha. So in the generalization, this looks as follows. This is a simple theorem. So we have phase gadgets, and we go to the size of n. So n denotes the size of our outputs, and then a ZX diagram realizes such a controlled phase gate with the size of n, about an angle of phi here. If we go from really 2 to n, and at each time have phase gadgets of degree 2, connect them to all possible combinations of the outputs, having phase gadgets of degree 3, connect them to all possible combinations, and so on. So we really go to exponentially many combinations over the outputs with those degrees. And at each degree, our sign flips. So for the phase gadgets with degree 2, we get a negative sign. For 3, we get a positive sign. For 4, we again get a negative sign, and so on. And the relation between this angle, which is realized by the controlled phase gate, and the value alpha, which is really then in the phase gadgets, is given by this. So this is kind of an exponential relation. So when going to higher and higher number of controlled phase gates, the actual values of alpha get exponentially small. So now, since we can use this theorem now for detecting multi-controlled phase gates over the output, we can adapt the extraction algorithm we have for graph-like diagrams to recognize those patterns of phase gadgets on the output which correspond to a multi-controlled phase gate. And there, since those exact patterns do not occur very often, we can somehow guide a bit the extraction algorithm to identify as many of those patterns as possible. For instance, this is simply possible if we have a phase gadget where the actual value of the phase gadget matches and the value of the output here matches, and this one not. We can simply unfuse the unwanted part of the phase towards a gate on the output, and we end up having everything we want for the multi-controlled phase gate here in the diagram. So as an example, we have a phase gadget of minus pi over 4 connected to an output with pi over 4, and here 3 pi over 2. So we don't want this 3 pi over 2. We need pi over 2 for extracting the phase gadget. So we would extract the pi over 2 phase as an RZ gate, and then we can extract the rest as a controlled phase gate here. And we can also use kind of a gadget unfusion if the phase in the gadget doesn't match what we want as a phase alpha. So then you may remember there's this gadget fusion rule in graph-like diagrams, which was used quite a lot to optimize non-Clifford spiders in diagrams. So if phase gadgets have exactly the same neighbors, we can fuse them together. But of course, this is kind of the reverse. We can unfuse this also again. So we have a phase gadget and we split it up into two different complementing phase gadgets, where if we would fuse them, they would exactly sum up to beta. And as an example where this might occur is here the following. When we have, so this structure here, the structure has every phase gadget we would need for a 3-qubit controlled phase gate, but this phase here of this phase gadget, it would need to be -π/4 instead of π/4. And then we can use this rule. We can unfuse this towards 2 phase gadgets, one phase gadget containing a phase of π/2, and the other phase gadget containing a phase of -π/4, which we want. And then we use all of those phase gadgets to extract the multi-controlled phase gate, and we end up with the single phase gadget here over the outputs. And as the last step, what we can also do is when there are phase gadgets entirely missing in the outputs. So here we again have the similar structure. We want to extract a multi-controlled phase gate on 3 qubits, but we only have this degree 3 phase gadget and one of the 3 degree 2 phase gadgets. So there are still 2 phase gadgets with -π/4 missing, one connected to 1 and 2, and one connected to 2 and 3. And what we can then do is we can basically insert those phase gadgets as identities. So those pairs are identities. They are connected exactly to the same neighbors. And if we would fuse them again, so -π/4 and π/4, they would cancel each other out. So this is basically an identity insertion here to complete this pattern. And then again, we can use all of the degree 2 phase gadgets with -π/4 in this phase gadget and the outputs to extract a multi-controlled phase gate. But then, of course, some of those phase gadgets which we inserted remain in the diagram here. And the nice thing is that this is actually G-flow preserving so also this insertion of phase gadgets on the outputs, this preserves G-flow. So at no point in the algorithm we are forced to abandon the procedure because we don't have G-flow anymore, but we can continue until we extract the entire diagram. Okay, so as a last step about this algorithm, regarding this time complexity of the algorithm, so if we have k being the number of vertices and n the number of in and outputs, then this standard diagram simplification usually runs in quadratic time in the number of vertices, and the standard extraction is dominated mostly by a Gaussian elimination procedure we need for eliminating or detecting optimal row additions for the C0 extraction. And if we do not insert additional phase gadget structures, so if we do not insert here, like shown in the last slide, new identities, then the worst runtime complexity stays roughly the same. So it stays the same. It is still bounded by this. And if we, on the other hand, use this synthesis algorithm with insertions, so we really allow those identities to be inserted, then what can happen at the worst case is that at each step of the extraction, we have only this highest degree phase gadget, and we want to extract it as a multi-controlled phase gate. So we would insert all the missing phase gadgets of lower degree, which are an exponentially many number in terms of the output. So this then becomes an exponential algorithm, which is not so good. So therefore, it may be useful if we apply this on circuits with many, many outputs to somehow limit the amount of how many controls can a extracted phase gate really have at some point. Okay, so as a simple example, how this could work, we have some input circuit, we feed it into the ZX diagram simplification and get this as a simplified diagram. And then we use our modified extraction algorithm, which specifically looks for this multi-controlled phase gates. And we get kind of an extracted circuit out of this, which contains controlled phase gates here, here, and here. And this is not a very sophisticated circuit so far. This is just a QFT, but this is already something Qiskit cannot do. If you give it a decomposed version of a QFT, it cannot reconstruct those controlled phase gates. And this is quite nice that this already does it. And our algorithm somehow also finds the optimal number here of controlled phases, which we need for a 4-qubit QFT. Okay, so far for the ZX synthesis part. I would now go on quickly how we can map this to the neutral atoms hardware. So now we have a gate set which has RZ rotations, controlled phases, and those Hadamards. And those Hadamards are still not implementable on neutral atom hardware, so we need to further decompose them. And how we decompose them is by doing something like this. So we group our gates into alternating layers of either single qubit gates or multi-controlled qubit gates. And then we decompose each single qubit layer into some sort of local Z rotations alternating with those global rotation. And you see here we do this global rotation about a negative angle, and here we do it about the same positive angle. So if we don't apply any RZ gate here in between, this corresponds to the identity. So this does nothing on qubits which are not, which don't have an RZ gate here in between. And we use two different decomposition strategies here, which are from another paper, which is not by us, which came out also just recently, a year ago. And they introduced this axial and transversal decomposition for addressing this problem. So as a first step, we have this arbitrary single qubit rotations, which we can decompose to RZ, RY, RZ. That's very standard. And then the RY itself, it gets decomposed like this in the axial decomposition. So what a global gate looks like, it basically applies this local rotation on each of the individual qubits. So this is a separable gate, and each individual gate can be described with this term. And this theta is the global pulse we need to apply for this global gate. And this phi basically defines us an axis in the Bloch sphere about which we rotate. And if we set this axis to 0, we get an Rx gate about theta. And the axial decomposition now simply decomposes the Ry gate into a global Rx rotation about -π/2, an Rz rotation about the angle theta, and another Rx rotation about π/2. So for all qubits where we don't have an Rz in between, those cancel out. And otherwise, we implement this decomposition. We want to implement this gate here from the ket0 to the state here. And what we can do is to decompose this into this Rx global rotation about -π/2, then the actual angle, and then again the global rotation about π/2. Now this is already, this is quite useful, but it is not optimal because what in the end determines the length of this global rotation gate is this angle theta here in between. And we can still find other decompositions which are faster, which have a smaller value of theta. And this is the transversal decomposition. So when we talk about the transversal decomposition, we mean a decomposition which is like that. And there we have global Ry rotation. So global Ry rotation is simply if we set this phi here to pi over 2, because the R gate in principle is a rotation about some axis in the xy plane. So if we have set this to pi over 2, then we can decompose this scheme to have a minimal value of this angle theta. So we then have a global rotation about minus theta half. Then we have a fast RZ rotation, and then we have another global rotation. And you see that in total, we don't exceed, we exactly have this angle theta in total, which we need as a global pulse. So this is minimal in terms of the global pulse, and that's because in the following, in our evaluation, we only use this transversal decomposition because it's optimal in the global pulse, and we want to optimize for global rotations. Okay, so if we do this on one of our circuits, it basically looks like this. We go through the gates here, and we put them in layers, so alternating single qubit and two qubit or multi-qubit layers, and we decompose the single qubit layers into RZ and global rotations. Now, for evaluating how this could be useful to neutral atoms hardware, we did some estimate of how long a circuit takes to be executed on neutral atoms hardware. And we did some assumptions. So we assume that the parallel so that RZ gates in parallel can really also be executed parallel on the neutral atoms hardware, but that controlled phase gates can only be executed sequential, because usually if we have two or more atoms in Rydberg state, the surrounding qubits are blocked and we cannot apply anything on them. So as a next step, we assumed that the gate execution time, both for the RZ, also global rotation and controlled phase, increases linearly with the rotation angle. So the smaller the rotation angle we actually rotate on hardware, the better. And our basis gate set is then here the RZ, which has a runtime about some 100 nanoseconds, depending on the actual angle. And the global gate looks like this. And this is in the range of microseconds, so it's an order of magnitude higher, usually. And the third is the controlled phase gate, which has been experimentally realized also in a similar scale than the fast RZ rotations. This is because this greater equal sign here means that this 100 nanoseconds hold for the 2-qubit case. For the 3-qubit case, it has been experimentally shown that it's about 400 nanoseconds. But as I've shown earlier on the slides, this more or less scales linearly. So this is still way beyond this 100 microseconds. So we ran a couple of circuits from different benchmarks through our synthesis algorithm, where we first used different synthesis algorithms and then used this global decomposition strategy with the transversal decomposition. And here we had 5 different approaches. So first was kind of the Qiskit native decomposition of a circuit into controlled Zs and U3 gates. And here, because we already know that this is quite inefficient for many circuits, especially if they control, if they have many Toffoli gates or something like that, which can be more or less straightforwardly implemented on neutral atoms hardware by just placing the target on between two Hadamards. We therefore used another non-ZX strategy, which we call the node decomposition strategy, where we simply go through the circuit and replace every controlled gate, which we cannot implement natively on neutral atoms hardware, with a neutral atoms equivalent. So like the Toffoli and CZZ and Hadamard on the target. This is a classic example of this. And then we had 3 different ZX approaches. So this ZX default approach is simply the standard simplification and extraction scheme. This ZX no insert is the algorithm which runs in the same worst case runtime complexity, so where we don't allow this additional identity insertions. And ZX with insert is the full algorithm I've shown. And those benchmarks were quite different regarding the circuit. So the cousin bench usually contains entire quantum algorithms from quantum chemistry or something else. Also the HHL algorithm is in there. So these are complete algorithms, whether the last 2 ones, they are more like specific parts of an algorithm, like the oracle. So those algorithms and those circuits, especially in the last, they are already consisting of like the optimal sequence of Toffolis. So our algorithm performed quite good. So the full algorithm in total. So we were able to reduce the total circuit execution time on neutral atoms hardware quite a lot, but it didn't work out in any case. So especially if we have those already optimized versions here in this benchmark, of course, it didn't work so well for the ZX no insert approach, and most notably this no decomposition strategy yielded the best results because we simply went through the circuit and replaced every Toffoli with the corresponding neutral atoms element, and thereby we kept the optimal number of multi-qubit gates. So this performed very well here, but in other cases, our algorithm was way better here. And if we go more into detail on this, what really our strategy yielded for individual circuits, we have here this no decomposition strategy as one column, and on the other column, the ZX with insert, so the full algorithm. And we are comparing how many global rotations we get, how many controlled phase gates we get, and how many multi-controlled phase gates we get from the synthesis algorithm and the decomposition strategy. And what we can see is that sometimes we are really able to trade those global rotations against controlled phase gates. So this is a really nice property that in some cases we have many single qubit gates which gets absorbed simply because we use controlled phase gates and multi-controlled phase gates. And sometimes this was quite drastic, like here in this algorithm, but on the other parts, sometimes it didn't work out very well. That's also the case that in some parts, really, this very naive strategy yielded already the best results regarding those global rotations. But on another level, which I find quite interesting, is that we were already able, with this approach, to synthesize multi-controlled gates out of a circuit where at the initial part we didn't have any multi-controlled phase gates. Because here, this column, because we don't change the amount of controlled phase gates in the circuit with this strategy, this column and this column, they more or less represent the original circuit. And you see that in those cases, we didn't have any higher order controlled gates, and our algorithm ended up with having those controlled gates in the end. So this then served as some kind of tool to identify those higher order structures in the circuit. So I said it didn't work out that well in some cases, and this, in my opinion, is highly dependent on how our graph looks in the simplification or after the simplification, because here I plotted kind of an optimal result. So in this case, we have all the phase gadget in one layer of the extraction. So we start from the outputs, we extract everything here, and then we have only phase gadgets connected to the outputs left, and then we can optimally determine how to extract all those phase gadgets. And you see we have here like eight gates, 8 controlled gates as an input, and we end up having 8 controlled gates as the output. But on the other hand, in many circuits, of course, it's not that easy. So we have many gates depending on each other, which somehow also gets reflected then after this diagram simplification, that we have phase gadgets which are only connected to inputs, phase gadgets which are only connected to outputs, and also to both, and some spiders in between. So it's not that easy to have all phase gadgets in one layer. And what happens then in the extraction is that we are able to kind of synthesize the optimal gates if we only consider here the Hadamard and the multi-controlled phase gates. But you see that the extraction also adds some kind of unnecessary redundancy here. So we have some controlled Z gates here, which we don't really need. And this, of course, it happens a lot, and it happens more if we go to more complex diagrams. So to sum up, we have this algorithm, which is based on graph-like ZX diagram, to synthesize any quantum circuit to this gate set, like Hadamard, RZ, and controlled phase gates. And if we then further decompose the Hadamards to global rotations, we have shown that we can get some potential benefit for optimizing circuit execution time on neutral atoms hardware. And the algorithm by itself, the synthesis algorithm by itself, I think it's already quite nice because we can somehow use it to detect these higher order controlled gates in the circuit, even if none of them were present in the circuit before. And possible improvements, I already talked about that in the last slide. So it would be really nice to further look into how can we really simplify those graphs to have as many phase gadgets in one layer of the extraction as possible. And this would correspond naturally also to G-flow, how we can have as many phase gadgets in one layer of the G-flow. And also another thing is that one can also, of course, come up with good heuristics for this gadget insertion in the extraction. So because now we did a very naive approach, we simply inserted all missing phase gadgets every time. And maybe there's also some efficient strategy to determine whether we really need to complete the phase, the multi-controlled phase structure in some cases, or if we just resolve those phase gadgets with the usual pivot eliminating strategy. Okay, so that's, I think, so far the talk from my side. And now, if you have questions, I'm very happy to answer them.
Okay, I guess everyone can give their claps, whether it's a clap emoji or a real clap. And yep, the floor is open to any questions. I had a question about the neutral atom hardware,
Yeah,
which was,
sure.
we have these multi-controlled phase gates, and is the runtime of these multi-controlled phase gates is it worse than the higher number of controls you have?
Yeah, it's a bit worse. I don't know if you, well, okay. Sorry, somehow my slides just got stuck. I think. Oh, I'm sorry. Okay.
That's okay.
Apparently, it just quit. I think there were at the very beginning, I had this graphic here, right? That it somehow increases linearly the runtime of gates. So it's at least it's expected. That's from a paper where they say, yeah, those values here, they are not experimentally realized so far, but they're theoretical results from optimal control theory, how fast we can implement those gates. So I would say that for the CCZ and the multi-controlled phase gate for 3 qubits, it's already fixed that it is implementable with 400 nanoseconds. But for the others, this hasn't experimentally shown, but it's theoretically possible.
Oh, I see.